In the last video, we used a simple model to predict the size of a population of creatures. That model had two ways for creatures to come into existence. The first was a spontaneous birth chance, which allowed creatures to pop into existence without any parent. The second was a replication chance, which allowed a live creature to create a copy of itself. In this video, we're going to make the model more realistic by completely getting rid of that spontaneous birth chance, which we know is unrealistic for complex organisms. Along the way, we'll build some graphs to take a closer look at how replicating populations behave with or without a spontaneous birth chance. We'll actually have two kinds of graphs. The first kind will track the number of creatures over time in a simulation. These number over time graphs will be a bit different each time we run a simulation, even if the settings for that simulation are exactly the same. Our second kind of graph will take a bit longer to build, but it'll help us understand what these number over time graphs have in common, and even predict what we'd expect the graph to look like before we run a simulation. For this second type, instead of plotting data from a simulation, we're going to graph a function where one quantity depends directly on another without any randomness. So the first step in creating this graph will be to tweak our equation from before and make it into a function equation that lets us plug values in and get values out. The starting point from before was to set the total birth rate equal to the total death rate. When these are equal, we expect some creatures to die each time step, but we expect the same number to appear to replace them. The overall expected change in the population would be 0. So how can we extend this thinking to make a function equation? Well, instead of assuming the birth and death rate are the same, we can subtract them to get the overall expected change. For this, we'll use the symbol delta. If you add the ones that are born and subtract the ones that die, you get the total change. The total expected change will still be 0 some of the time, but now we have a foothold for thinking about cases where we do expect an overall change, which is good because, as you can see, the number of creatures does change pretty constantly. And our equation is starting to look like a function equation. The last step is to write the birth and death rates in terms of the total number of creatures, and then we'll be able to draw the graph. We did this in the last video, but let's run through it again. We can break the total birth rate into the spontaneous birth rate, which we're going to get rid of later, plus the replication rate, which is the chance of a single creature to replicate at a given time, multiplied by the total number of creatures. Similarly, the total death rate is the chance for a single creature to die, multiplied again by the total number of creatures. Finally, we can rearrange things to see more clearly that the replication and death chances are competing to determine the expected net change per creature. This difference is going to have a big impact on the population. So now we have the expected change written as a function of the number of creatures. For any number of creatures n, we can determine the expected change delta. Alright, let's look at a specific situation. Let's make the spontaneous birth rate 1, so each time step will see one brand new creature pop into existence on its own. The death chance for each creature will be 0.2, so each living creature will have a 1 in 5 chance of dying each time step. And to start out, let's leave the replication chance at 0. Alright, now we get that satisfying feeling of plotting all the points and making a curve. When we have 0 creatures, the expected change is equal to the spontaneous birth rate, and as n increases, the expected change decreases by 0.2 per creature. Notice this point here where delta is equal to 0? That's our old friend, the equilibrium point from before. At that point, which is 5 creatures in this case, we don't expect any change on average. If the number of creatures goes below 5, we'll then expect a positive change at the next time step, pushing the population back toward 5. And if n goes above 5, we'll expect a negative change, again pushing it back toward equilibrium. To toss another vocabulary term at you, this is known as a stable equilibrium. At this point, the birth and death rates are in balance, and it's stable because if we deviate from this point, the system will tend to go back. It's self-regulating, as if there's a rubber band pulling the system back toward equilibrium whenever it strays away. So what kind of number over time graph will this produce? If the simulation is at equilibrium, our best guess is that there will be zero change in the next time step. Right, that's what this point means. The expected change is zero. So over time, what we expect is for the simulation to stay at the equilibrium number. This straight line might seem naive because we've seen how these simulations can fluctuate like crazy, but if we graph the data from a whole bunch of simulations at the same time, we can start to see that this really is a pretty good guess for what to expect on average. Now, what happens if we add a replication chance? The slope of the line changes, and so does the equilibrium point. Overall, though, things are pretty much the same. Things get interesting when the replication chance is the same as the death chance. In this case, we get a flat line and the equilibrium disappears. If you saw the last video, this is where we divided by 0 and our equation broke. There is no equilibrium. What about number over time graphs in this kind of situation? There's no more equilibrium, but we can still say something about the growth rate. That's why we built this function equation in the first place. No matter how many creatures there are, the death and replication chances offset each other, and we expect the population to constantly grow at the spontaneous birth rate, which in this case is at 1 creature per time step. So, starting at 5 creatures again, the expected curve looks like this. Steady growth. And just like before, we can convince ourselves that this is a good guess by plotting the results of lots of simulations on top of each other. There's something extra to notice here though. That rubber band effect of the stable equilibrium is gone, so we see this spread develop as time passes. Things get even more interesting when the replication chance is higher than the death chance. We get a positive slope, and this reverses that rubber band effect. When the number of creatures goes up, the expected change also goes up, causing the number to go up even more in the next time step. The two feed off of each other, going up and up and up. The result is exponential growth. It's slightly more involved to show this precisely, so I'll link to some other resources in the description in case you want proof, but once again we can look at a bunch of simulations to confirm the result. Notice how the number of creatures is much higher here. This explosive growth comes from that tiny bump in the replication chance. Also, the spread is even worse this time because of the reversal of the rubber band effect. Now, let's finally set that spontaneous birth rate to 0. We still have that reverse rubber band effect, where the expected change gets bigger and bigger and bigger, but if the population is ever 0, it gets stuck. There are no creatures to replicate, and none are going to be born spontaneously. This is called extinction. It's over for those creatures. So, if we start with a few creatures, 2 in this case, some simulations will grow exponentially and quickly be in no danger of extinction. But others will get unlucky and die out, never to come back. Creatures that depend only on replication are on a knife's edge, especially when their numbers are small. So, if complex organisms can't appear spontaneously, and they can't replicate unless they already exist, how do they get their start? We'll find out as we keep building our model in the next video. See you then. Hey, thanks for watching, and thanks to everyone who's already become a supporter on Patreon, especially the one, the only, Jordan Scales. If you think you might like to contribute toward making more videos like this possible, have a look at the Primer Patreon page. Also, if you'd like to discuss more deeply than is usually possible on YouTube, check out the Primer Learning subreddit. Right now, this channel isn't big enough to put clickable links right in the video, but they're in the description. Again, thanks for watching.